Bangalore Theory Seminar. Today we have Dr. Pravesh Kothari. He's a faculty at Princeton University. Previously, he was a faculty at CMU. He had he did his PhD at UT Austin, and he has won numerous awards. To name one, he recently won the Pressburger Award. Today, he's going to talk about sparsifying sums of positive semidefinite matrices. And I guess that's it.
Okay. Yeah, thank you for having me. Thanks especially to Anand for arranging this visit at such short notice. Really excited to be here. And thank you all for coming on a holiday, it seems. I'll make it worth your while. Oh no. I take back all the good things I said. Okay, so yeah, I want to tell you about this this work on proving a new sparsification theorem. And yeah, it's joined with some amazing collaborators. Arpon Basu is a super young student. He's just in second year. He's amazing. Young, used to be a postdoc at Princeton at the time, and now he's a professor at Carnegie Mellon. Raghu, I suppose all of you know. So what I want to do is first remind you of like some sparsification theorems that you already know, and then tell you why you might care about generalizing them, and then how you might generalize them. Okay. Okay. All right. Let's talk about graph sparsification. Many of you might have seen this theorem before, but I'll walk you through it because this is our natural starting point. Okay. So the whole underlying motivation, really came from algorithms, which is strange because this area has really now affected so many other things in computer science and beyond. But the initial motivation was like, I have a dense graph. Can I somehow approximate it in some relevant sense with a sparse graph? And here, density and sparsity is in terms of number of edges appearing. Okay. So like, and why might you care about it? Well, I guess, like I said, initial motivations were to speed up algorithms. If I could do this like in some relatively intelligent, fast way, then I could replace a algorithm running, let's say, in quadratic time in the number of edges. The running time will drop substantially if the number of edges become much smaller. This is like the overall idea, and maybe the quality of solution would be lost a little bit only if I can maintain approximation in relevant senses. Okay. So let me tell you what quality measure we will care about today. And this quality measure itself is like maybe a second gen product, arising in the early 2000s, but it's going to be the right one for us. So I'm going to say that a graph H on the same vertex set as graph G is a spectral approximation to graph G if this PSD inequality holds. So L is the Laplacian matrix of the graph. If you don't know what it is, you should just think of it as, if I take a quadratic form of the Laplacian matrix, it just gives me the size of the cut. Like if it's on a 0, 1 vector, it gives me the size of the cut. Okay, so you should think of Laplacian as the natural matrix to write down if I want quadratic forms to mean sizes of cuts. Okay, and more syntactically, it is simply taking for every edge, right? You just shift it by the diagonal matrix of the two vertices it depends on. And then instead of, you can think of adjacency matrix as adding indicators of edges. For Laplacian, you add like the shifted indicators where you also have like, +1 each on the two diagonal entries corresponding to the edge. That's the other way to think about it. But really, I implore you to think of it as a natural matrix whose quadratic forms relate to cuts. So 0, 1 quadratic forms, in fact, are exactly equal to sizes of cuts. Okay. So what this says, if you just think of it as, so what is this inequality? It says that, if I look at these, so these are positive semidefinite matrices, which is not surprise, cut sizes are positive, right? Let's say unweighted graph at least. So what this inequality says, at least just for the cuts, is that all cuts of H are within 1 plus minus epsilon multiplicative approximation to the cuts NG. Okay. Now notice that, because the sizes of edges are going to obviously vary, like, I'm going to replace eventually n square edge graphs with n edge graphs effectively. The cut sizes, of course, will drop because there are fewer edges. But I'm going to allow placing weights on edges for this to be meaningfully possible, right? So your goal is to find like a weighted collection of a small number of edges to get this graph H such that every cut, and in fact, every quadratic form, which now goes beyond cuts, that's the spectral part. I don't just care about 0, 1 quadratic forms, I care about all quadratic forms now. I want this inequality to hold. Does it make sense? Like, this definition? I'm happy to write on the board, etc., to clarify it if it's not clear. Okay, great. So, yeah, so this question arose, in a very combinatorial context in the work of Bencher and Karger. Actually, the paper is from 93, but I think maybe the journal thing is 96 or something. Many of you might have even taught this, like, this is whatever, the sequence of 3 amazing, beautiful short papers of Karger, beginning with, the cut sparsification result and things like that. So this is, I guess, the second in the result due to Bencher and Karger. And they showed that, if I don't care about the spectral sparsification, but cut sparsification, that's like quadratic forms on 0, 1 vectors, then I can indeed approximate any graph by a weighted graph on just about n log n edges, right? So I'll care about dependence on epsilon, but it's always going to be 1 on epsilon square. So, we can even forget about it and just think of epsilon as 0.1 for the purpose of this talk, okay? So I just think of dependence on number of vertices. And then, this result says that n log n edges are enough. And then, eventually people discovered that, so they were interested in like algorithmic applications, like, how do you compute min cuts fast, for example? This was one application they had. Later on, Spielman and Teng discovered that actually there are more applications to so-called Laplacian system solvers. So like certain kinds of linear equations which you can hope to solve very, very fast. And they observed that one way to do this is to make the equation matrix sparse. Then, somehow, if each equation is sparse, you could do some like iterative methods very, very fast. This was like the overall idea. And they observed that for this, you don't need just cut sparsifiers. Like, equation solutions don't need to be 0, 1. That's the whole intuition. But, spectral sparsifiers suffice. So this stronger notion I wrote on the previous slide suffices. And so then they observed this. And then, in this very nice paper, I mean, they already had a construction. It was more complicated. But Spielman and Srivastava, they had like this beautiful construction that you can teach in courses. Takes half an hour. It's a wonderful introduction to matrix concentration inequalities. In fact, that's how I teach matrix concentration, the first lecture. They showed that spectral sparsifiers exist with n log n edges. Okay, that was, so they upgraded the guarantee of Bencher and Karger. And actually, maybe even beyond the upgrade, they significantly simplified it, right? Like it's essentially one of those things where you write down the matrix concentration inequality and the proof writes itself. Like once you observe the inequality, everything just happens on its own. There is nothing almost you can do. All the choices are dictated by the inequality itself. Okay. So that was like, the n log n sparsifiers, but then there was like this big question, whether you can get down to order n. And, I myself, often I'm confused why we should care about some log n's, but this log n turns out to be an extremely worthwhile quantity to try to reduce. It led to so many things. And, Batson, Spielman, and Srivastava had this great, amazing result that showed that, in fact, order n sparsifiers exist. The main difference, I don't want to say too much about it. You can ask me later if you want to hear more of the story. But Spielman and Srivastava's result was this independent sampling framework. It's like, you for each edge, you're going to choose some probability. That's going to depend on how important the edge is, but then you're going to sample it independently. And it turns out that this framework provably fails. And, if you want to see some basic intuition why, it's basically like, coupon collector type things. If you have like n objects, all of them are equally probable. I still need n log n tries to get them all, right? Like that's the intuition. So order n is simply impossible with the kind of tricks that people were doing earlier. And then, so BSS invented this powerful method called the method of barrier functions to get this order n sparsifier result. So it's an amazing result. It led to lots of new things. It's even in some sense a precursor to this sequence of results due to Marcus, Spielman, and Srivastava, which are also sparsification results actually. But anyway, so that's graph sparsification. It has a wonderful story and I could go on for hours about it. But that's not the question we're going to think about. We're going to try to first, view it as an instance of a more general question, and that question will be our interest today. So the first observation is that if you look at the Laplacian matrix of a graph, it can be seen as a sum of rank 1 positive semidefinite matrices. Rank 1 matrices are PSD if and only if they are symmetric. So rank 1 symmetric matrices, right? Like positive weighted sum of rank 1 symmetric matrices. And this simply is the observation that if I look at a single edge, the graph which has one edge, then its Laplacian is rank 1. And the Laplacian, like I told you, is a sum over all edges of each edge Laplacian. So, it's a sum of rank 1 matrices. The sum of rank 1 matrices matters because what you're trying to sparsify is the number of rank 1 terms appearing. So you can think of this graph sparsification problem as an instance where you have a positive semidefinite matrix. You want to approximate it spectrally. It can be written as a sum of rank 1 terms. And you want to basically sparsify this sum. You want to use a few rank 1 terms by maybe using weights if needed. But you want like this weighted sum of rank 1 matrices to be somehow spectrally approximate on all possible quadratic forms. This makes sense? Good. So once you observe that this is what graph sparsification looks like, you can ask, can I do this rank 1 constraint? Can I just have an arbitrary sum of positive semidefinite matrices and hope to sparsify this sum down? When and how may I do it? Okay, does it make sense, the question? Okay. So that's the question I'm going to be interested in today. You're given arbitrary positive semidefinite matrices, A1 through AM. They're going to be little n by little n matrices. Their sum is some AI, right? They're positive semidefinite. By the way, if you want multiplicative approximation, you need to deal with positive quantities. So you might wonder why this whole focus on PSD, but it's the only thing that kind of makes sense. Otherwise, multiplicative approximations don't make sense. Good. So your PSD matrices A1 through AM, they have the some AR, and you want to approximate spectrally in the same sense as we saw before by a smaller number of terms. You can use weights if you like. That's the question. Okay. Correct. Now we are dropping all rank assumptions, so AI might be higher. Okay, that's the question that we're going to be interested in today. Good. So it turns out that, this question is essentially completely solved already. Okay, so I can end the talk at 14th minute. So I guess this theorem is due to Silva, Harvey, and Sato, due to Michael Cohen. A bunch of results. Like the later on papers were basically building on this technology of Marcus Pillman Srivastava. This first paper builds on the technology of Batson, Pillman, and Srivastava, the result I showed you on the previous slides. And basically, all these people showed that there is a sparsifier for this sum with order n over epsilon square entries. So same result as graph sparsification. And in fact, the n log n one is word for word the same proof as the matrix concentration proof of graph sparsification. So that's like entirely trivial in that sense. And if you know graph sparsification, this result just follows. There is nothing about rank 1 that matters in that proof. And what these results are saying is that you can even remove the log n by an appropriate generalization. It requires some thought, but you can do it. An appropriate generalization of this previous results. Okay, so everything seems great. We have generalized it. We didn't even lose anything. So what are we doing? Okay. Yeah. Yes, exactly. Yes. Okay. So in order to understand whether this is a good bound,
graph you could have fictitious edges.
yes.
But here you are really subsampling in the sense that you're just sort of increasing the weights of some AIs and zeroing out the others. And
yes. Yeah. So that's what I can do.
in the graph you could have
all of them produce.
Yeah.
Oh yeah, that's a good point. I guess in principle it makes sense to find an approximation with, like, if you want to approximate a object by some simpler class of objects, rank 1 terms or whatever, then it makes sense to allow not using even like the original decomposition terms, etc. But once you go to this more general problem, that one is not reasonable, right? There's always a one-term approximation. So so we will always think of like using a subset of the expanding terms. Yes. Yeah, great question. Yes. Yeah, it's very explicit, right? In fact, our proof is of the same sort, so you will also see where it comes from. There's a natural notion of how important a matrix is, and the weight is basically proportional to its importance. That's the way you should think about it, okay? Let me give you something that you can, while I'm filibustering for the next 5 minutes, you can think about this. So, if you have like 2 clicks connected by a single edge, this edge is, of course, super important for sparsifying. If you drop it, the graph is disconnected, right? So this edge is super important. So you can see that there's some intuitive notion of how important edge is going to be for maintaining, like, robust connectivity of the graph. There's going to be an explicit way to measure this, and the weights will be proportional to it. For people who know the word effective resistance, it is the effective resistance. Okay. Good. So this is the theorem, that came out, and it's already tight, even for rank 1 terms. So what are we doing, right? So in order to understand what tightness means, let's maybe explore a little bit further, okay? Clearly, this bound is tight. But why did we say clearly? Okay. Why can't I hope to sparsify a graph down to less than n edges? Well, because we know that a graph requires n edges to even be connected, n minus one edges to even be connected, right? Otherwise you'll have a connected like a disconnected subcomponent, right? You can say, well, in any connected graph, I'm bound to need at least whatever about n edges. I can't hope to go below that, right? Like this is the so-called connectivity bottleneck in constructing a sparsifier. It's a qualitative bottleneck, right? Like you can think of sparsification as a quantitative thing. I want to approximate all cuts, right? This is a qualitative bottleneck because it's saying that I can't even maintain zero non-zero nature of cuts. Some cuts which were non-zero will become empty if I use less than n edges. So it's like blaming this quantitative question we are after, impossibility of it, on a qualitative value. That's the way you should think about it. Okay? Make sense? Great. So now, given that we have this intuition, you can see that this bottleneck really relies on the fact that I was sampling edges. Now I'm sampling higher rank matrices because I'm a sum of high rank things. One natural example to keep in mind of high rank matrices is, you are sampling a collection of edges together. So it's like a correlated sampling. You get to pick like a bulk of edges once or not at all. And that's one way to produce high rank matrices. But if you're sampling more edges, then less of them might be enough to, get to this connectivity bottleneck. So this objection will not actually apply in principle to high rank matrices. Okay. I'm beginning to build this intuition that for high rank settings, you should expect a better result. This order n is tight, but it's tight in a setting where it is not quite using the high rank nature. So you should expect a better result for high rank, but it is not known. This is where I'm going.
The sum of AIs
Yes.
is rather small.
Yes.
Like the graph I give you is only a small connected component.
But let's assume it's connected without loss of generality, right? Like you drop things which if yeah. So I'm saying like if you're less than if the sum itself is low rank, you can just drop the subspace that doesn't matter. So it's like without loss of generality that the whole matrix itself, the sum itself is full rank. The question is like what are the constituents like? Like I'm saying, in the context of graphs, you can, without the loss of generality, go to a connected component and sparsify it, right? Like you can forget about the rest of the graph. Okay, so this is the way intuition that, this connectivity bottleneck doesn't quite apply if your matrices are high rank. So you might, at least naively speaking, expect a better result if the constituent matrices are high rank. So that's the question, we are going to be interested in. We're going to ask what, if at all, is a bottleneck for this high rank matrix sparsification question that we have constructed before us. And can we do better if it happens to be much tinier than whatever this connectivity bottleneck that we discussed just was? Does it make sense, the whole goal? So the overall conceptual question is like, what is the right qualitative barrier for sparsifying sums of positive semidefinite matrices? Can it be much tinier than n? And if it is, can we somehow get sparsifiers with much less than n elements in the sum? Okay, good. So, I'm going to phrase the question as follows. So, this is now just a formalization of the question. So I'm going to maybe read it out, even though it's the same. I'm going to be given a fixed family of positive semidefinite matrices. Okay, A1 through AM. Then, so these are fixed once and for all. And the problem I care about is you're going to be given an arbitrary subset of these fixed, whatever universe. I want to sparsify the sum of this subset. Okay. In the same sense that we've been thinking about. And the way you should think about it is the generalization of graph sparsification. Why is it generalization? Think of the family of PSD matrices to be all possible n choose to edge Laplacians. Then every graph is a sum of some subset, namely the edges that appear in that graph. So you can think of graph sparsification as a special case where this family happens to be all possible n choose to edge Laplacians. Right? Does this make sense? The reason I'm doing this is because we already saw that order n is tight if I look at arbitrary Laplacian sum sparsification. So whatever my answer is has to depend on instance. I'm really going for an instance specific bound. In order to have a fixed instance, I'm going to fix a family of PSD matrices first, and then I'll show you that there is some qualitative barrier that can be defined naturally as a function of this fixed family, and that controls the size of the sparsifier. Okay, does it make sense? Yes.
The edge Laplacians, if I were to pick like key edges at a time.
Yes. Yes. Yes, yes. In fact, you'll see like the main application is this Cayley graph sparsification, where one can view each constituent matrix as a Laplacian of a perfect matching. And it turns out that setting occurs quite a while. In fact, that was the question we were originally interested in. And then we realized that there is a natural theory to build here in terms of, PSD sparsification. Okay, good. So, all right, so that's the main question we're going to be interested in, that it's not going to be the dimension of the matrices that controls the size of the sparsifiers. It's going to be something else, and what something else is our interest now. Okay. Good. So, all right, so it's a generalization of graph sparsification. We already discussed it. Now, naively, you might hope that for every sum of high rank matrices, even let's say omega n rank matrices, maybe you are like very ambitious n/2 rank matrices. I say n/2 because that's what perfect matchings correspond to. So we are still trying to follow our combinatorial intuition. You might expect that, maybe I can do much better than n here. It turns out, in the paper we give construction of counterexamples that high rank is not sufficient. Even, in fact, you can give a collection of omega n perfect matchings such that you can't even drop a single perfect matching and get a sparsifier. Okay, so high rank is not enough. Even though like intuitively it appears like it might do more than, what we were doing earlier, it's not. Okay, so it's going to be more subtle, and, we'll try to build up to an answer to that. Okay. So what's going to turn out is that, there is a natural parameter, and I'm going to describe that, and I'll spend like 5 minutes on this slide because this is the main definition. This parameter is, I'm going to argue is the right parameter, right qualitative generalization of this connectivity bottleneck that we saw for graphs. Okay. So let me, first try to view graphs in the following way. In any collection of n edges on n vertices, there is a precise sense in which at least one edge is redundant. Okay, let me explain how. It's redundant because there must be a cycle, right? It cannot be, it's not, it has n edges, so there must be a cycle. Take the cycle. In this cycle, I can remove one edge, but it doesn't disconnect the graph. There is another route to go and connect the endpoints of this edge. In that precise sense, in the sense of connectivity, this edge was redundant. I could remove that edge and not drop the connectivity of the graph. So you can think of little n as the precise threshold at which there is redundancy. Okay, I am going to generalize this notion of redundancy. Okay, this connectivity parameter says the following. I'm going to say that, so let's maybe look at the quantifiers later. First, just fix a collection of PSD matrices, A1 through AK or whatever. One of them is redundant if I can pull out one and dominate it spectrally by the sum of the others. Okay. Again, you should keep thinking of the graph case. This is like saying, so if I pull out one edge, the quadratic forms of this edge are basically, on the cuts that contain this edge, they get a +1, everything else is 0, right? So you're trying to say that in every cut that this edge contributed a non-zero value to, can you make sure that the rest of them at least contribute 1 all like together? So at least one of them should contribute +1. Okay? And you can say that, this is true for a cycle, right? Just because of this connectivity intuition that we just discussed. This inequality is more or less saying the same thing, except I allow a small constant slack. So instead of dominating AI itself, I allow you to take alpha to be a little bit tinier than 1. In fact, everything we do, alpha would be half or something. Like any fixed constant less than 1 is reasonable for us. So I'm going to say that AI is redundant for a sum AI in some subset T if one can remove AI and dominate it by the sum of the rest. This is like saying I can cover whatever was going to happen by this, qualitatively speaking, the zero non-zeroness level, by the sum of the remaining matrices. This parameter is the smallest K, such that for any collection of K matrices in my list, there is at least one redundant element. You should think of it as the analog of saying in every collection of n edges, there is an edge which is redundant. So I want the smallest k such that in every collection of k PSD matrices from my original set, there should be one which is redundant in the sense that I can dominate it up to this alpha scaling by the sum of the rest. Does the definition make sense? And hopefully you buy that it is not maybe too unrelated to this connectivity bottleneck notion for graphs. Yeah? Okay, great. So
what is the parameter we are tuning so that one edge becomes redundant? Like, does it have to be like, so more than one edges can become redundant, right? What is the parameter that controls
so this is a qualitative notion, right? Like all we are saying is that, k is the smallest number such that in every collection of k edges, there is at least one which is redundant. If one is redundant, you can throw that out and then, repeat. Right? In the context of graphs, for example, that's true, right? Like if you have n plus 1 edges, yeah, there is at least one edge, there are probably two edges which are redundant, but certainly one edge. You can take that edge out and then repeat on the subset. So we don't, there can be multiple matrices which are redundant, but we only care about at least one way for the definition's sake.
Right. Okay.
Okay, great. So the connectivity threshold is simply this parameter, but for some fixed constant alpha star. Like I said, alpha star like half would suffice for us. Okay, does the definition make sense? Okay. So the main result.
But not the case, right? Like if the other matrices could not spectrally dominate, you are leaving like up spaces. Like
uncovered. Yeah. So what your intuition is precisely going to prove that this is the lower bound of any sparsifier. Yeah. And the main result is that it's also an upper bound up to some polylog terms. This is the main result. So yeah, you're absolutely right. You're just looking ahead. Okay. So so this is the main result that, for any collection of PSD matrices, we can give a upper bound on the size of this epsilon sparsifier in terms of this n star quantity. So it's going to be n star times log n. So that's the dimension dependence, log of the dimension, times log n. That's the log of the number of matrices dependence. Okay. These two can be very different. In this context, they are like at the similar order in some sense, because in graphs, for example, there are n square edges and dimension is n. So logs are about the same. But there can be settings where log m is much tinier than log n. In fact, these are very interesting, where the dimension of the matrices is huge, but the number is small. And so what I'm trying to point out is that this result incurs a log cost in dimension and the number of matrices each. Okay, good. And by I won't even expand on this, but the intuition that Sid had, this is clearly a lower bound. In some sense, if there is no redundancy, then you need as many. You clearly need as many matrices as redundancy requires, because otherwise there's going to be some quadratic form which is not even qualitatively covered. Like it doesn't even have like, a infinity, like less than infinity approximation in some sense. Okay. So, because of this, the bounds are optimal up to this two log terms. And in fact, in the end, I will come and ask whether these are necessary. Good. So I want to give an application, an example application to show that, we are not just doing empty theory building. In fact, this was the main motivating example for us. So let's say I want to sparsify Cayley graphs. So, maybe some of you, if you haven't seen Cayley graph, it's a very simple object. It's a specific kind of algebraic graphs. Okay. So take any group. Okay. You can think of numbers modulo p. So addition modulo p as your group. A Cayley graph is described by a subset of group elements that we call generators. So it's a subset of group elements, let's say, some subset of numbers modulo p that you took. And then you can imagine labeling the vertices by group elements. So there are as many vertices as group elements. And each edge corresponds to basically addition with one of the generators. So each edge you can imagine has like a label on it. The label says which group element you should add to get the neighbor after following that edge. So there is clearly an algebraic meaning to it. One, graph that we often see, all of us have worked out, is the hypercube. It's a natural Cayley graph. You can think of it as the Cayley graph on the group F2 to the n, with generators, the standard basis vectors, E1, E2, En. So that's an example to keep in mind. But, you can define Cayley graphs on any groups. And, if you don't know much about them, all I can say is that, almost every interesting graph that we can construct is a Cayley graph. All Ramanujan graphs are Cayley graphs, all the, expander graphs, etc., etc. Like, it's basically the main algebraic way to construct graphs with nice properties, pseudo-random properties. Okay, great. So Let's say I give you a Cayley graph. So it's described by a group G. By the way, I'm not caring about whether it's abelian or non-abelian. So it could be whatever. You can take the symmetric group for all I care. Results will make sense there. And, it has some set of generators S, right? I'm going to work with undirected graphs, so it's a symmetric set of generators. So, if G is present in S, then G inverse is also, so that I can follow it backwards. It's not a directed edge. I want to approximate it. That part is okay. I can just apply Baxton, Spearman, Srivastava. But this time, I want my approximator to itself be a Cayley graph. Because maybe you want to take a Cayley graph, make it smaller, but still want to maintain the algebraic structure that you started with. You might care about this. I'm actually, just going to ask you to think that this is interesting because I was convinced it's interesting. I can tell you why you might care about it at the end, but that's kind of a distraction. Okay. Hopefully you agree that there are reasons to have algebraic structure, and you might want to keep that structure around in the sparsifier. So that's like the overall goal. Okay, this makes sense. The group is the same. Everything is the same, but I'm going to allow weights on the generators. The number of generators will be smaller, but for the same reason as in graph sparsification, we'll have to allow weights. There's going to be a weighted Cayley graph, if you will. Okay, good. So yes, I have slides. Yeah, all the slides are by Raghu, so he's anticipating what I'm going to do. Good. All right. So that's the picture of Cayley graph. And I guess I already told you all of that. Good. Yeah. You also see examples, the hypercube, the Ramanujan families, expander constructions, codes, etc., etc. Won't tell you much about that. But I'll show you how this framework that I just showed you actually gives a sparsifier with log to the 4 generators. And so this question, has been around for a while for the case of hypercube, Cayley graphs on hypercube. So, the usual hypercube is Cayley graph with fixed generators, E1 through En, but you can define many Cayley graphs on hypercubes. In fact, people do study it. These are, again, very interesting examples, integrality graph families and so on. It turns out that for the case of F2 to the N, you can do something very combinatorial. And, this very nice paper of Khanna, Putterman, and Sudan, they did it last year. I think it's 2 years ago. They showed that, in fact, there is a log n size sparsifier, where n is the size of the graph. But that was the only result that was known in this direction. So Cayley graphs on F2 to the n were known to have sparsifiers, which were, roughly logarithmic in length up to log factors. But for any other group, we did not know even like a sublinear bound. And so what we're going to prove is that there is a log to the 4 size sparsifier for every Cayley graph. And I should say, there is a related work due to Putterman. I think the citation is also not correct. There's Siddhant Mohanty, Tim Shea, Louis Putterman, Rachel Zhang. One more person, I forget. Yes, yeah. All the mistakes are Raghu's. I'm on video saying that. God sake. Okay. Independent work, they also basically prove the same result. I think maybe it's log to the 4 is log to the 5 or something, but their proof is quite similar, and the result is basically the same spirit. So there are 2 papers. If you don't like ours, read theirs. Okay, good. So let me maybe make one point. If you're aware of this so-called alone-Reutemann theorem, it's like a classic theorem in this area. It says that if you look at random Cayley graphs. So if I take like log n generators in a group of size n, and I just take a Cayley graph with this, then it's going to be an expander. Okay? Of course, like there are like expander graphs with just constant number of generators, but this is saying that in any group you can get an expander with like log n generators. Okay, you can think of an expander as a sparsifier for the complete graph. In fact, that is the point at which like all the spectral sparsification theory starts. There's a generalization of the fact that a complete graph can be sparsified, can sparsify arbitrary graphs. There are results that show that this log n is necessary. There are abelian groups where you cannot have sparsifiers, cannot have expander graphs with less than log n generators. Okay? So unlike the usual graph sparsification case, you can't hope to go below log n even for the complete graph here. So you can think of this as telling you that, you can think of what we are proving as some kind of analog of alone-Reutemann. Alone-Reutemann shows that expanders can be sparsified down to log n and no better. We are proving that every Cayley graph can be sparsified down to log to the 4, potentially better, but not better than log n. Good. All right. So Let me maybe tell you at a high level about how this result works, and then I'll come back and tell you about the main ideas in the proof of the main result. So if you believe the framework we just generated, we have reduced the problem down to simply estimating this connectivity parameter. Right? Like what else can we do? We've characterized the size of the sparsifier up to this n star quantity. We lose like some log square on top of it because the number of matrices, in the context of groups is just the group elements. Size is the group size. So that's just like log square in the group size. So all I have to do to prove this result is to prove that this n star quantity is going to be log square. And that's basically what we prove. We actually don't know how to analyze it for constant alpha. But it turns out that, for any constant alpha, I can get a upper bound by analyzing, this n star quantity for a smaller alpha. And we show that, if we make alpha 1 over log n, we can get a simple, very simple algebra gives a proof that for this alpha, the connectivity parameter for this Cayley problem is log n. Okay. And so it turns out that because the alpha is not a constant, this 1 over alpha goes into our bound for the n star quantity. So we get a log square bound, and that's basically how overall we get the proof of the Cayley result. Good. So good. Yeah. So let's make this point. I guess I said it earlier, but it was informal. So look at all the edges that correspond to shift by the same group element. Then notice that this is a perfect matching. Right? And so, each group element corresponds to sampling all edges that correspond to it. That's clearly a perfect matching. By the way, each group element, when I say it, I mean G and G inverse. It's an undirected. Okay. So, so sampling a generator or like trying to take a subset of generators is like saying, take a subset of this fixed perfect matching. So, like I was saying earlier, this is the example of high rank sparsification because you're in correlated sampling, where if you pick one edge, you must pick all the edges that correspond to the shift by the same group element. Yeah? Great. Okay. So let me, roughly tell you how the proof of the main theorem. Everything is very simple. Okay. So I can actually more or less give you, at least the main idea quite easily. Okay. And
so somehow like the structural properties of graphs haven't shown, even of the Cayley ones haven't shown, but you're saying that's not required.
No, it is going to show up. Like this main lemma is going to rely. It's I can even tell you right. I'll show you it later. Maybe if I don't get to it, I'll maybe say one sentence right now. This lemma is simply going to be the following observation. That for any group you can define a notion of a generating set. Like the smallest number of group elements so that I can produce every other group element by like some linear combination. Okay. There is a notion of a minimum size of a maximum size of a minimal generating set. A set is minimal if you can remove things and you can still generate the whole group. You can think of all possible minimal generating set and take the maximum size. Okay. It turns out that this is still logarithmic for every group. This is not so surprising. It's some counting argument. Like fixed log n group elements, take all possible 0-1 combinations. There are exponentially many. So either you hit a redundancy or you covered everything. That's it. Okay, so what does it mean? It means that I can always write down any group element as a combination of at most log n other group elements in my set I'm looking at, and you can like combinatorialize it. You can show that this fact actually gives you the spectral upper bound condition I was writing. So it's not it's a routing proof, right? Like I'm routing an edge with a path, and then I lose a log n because if I do a naive routing, length of the path is what I lose in the routing, if you know what I'm talking about.
Yeah, it's like the diameter of Cayley graphs is small, so it's the same.
That also is the same observation. Yes. Yeah, so it's very simple. So there is some property that goes into it, but like pretty basic. Nothing very deep. Yeah. Okay, good. So let me give you the proofs to the main theorem. This way I will also clarify where the weights come from, why they are very explicit. Okay, so remember our goal, right? We are given this fixed family of matrices A1 through AM. An instance of sparsification with these matrices as the family is described by a subset T of these PSD matrices. I have the sum of these PSD matrices, and I'm going to sparsify it down. I want to take the subset T, maybe keep a smaller thing with some weights, so that the weighted sum is a spectral approximation to the sum of AIs in T. So, our method is basically the same that it has been for 20 years. Okay, we are going to basically, compute a notion of importance for each of these AIs in the sum. These importances, have interpretations. So if you heard of the word leverage scores, that's what it is. If you heard of the word effective resistance, that's also what it is. Some natural notion of importance. I'll describe it very explicitly. None of these interpretations are important. Okay, you'll see how supernatural it is, how very natural it is. I don't mean super. There was unintentional. So the method is going to be leverage score sampling. Sample each AI with some probability, which proportional to how important it is. And then the analysis reduces to showing what is the number. Like I have to argue two things if I sample like this. So I'm giving you a particular sampling scheme. It's an independent sampling scheme. Each AI is sampled independently with some probability p sub I. I have to argue why is it a sparsifier, and I have to argue why did I sample a few elements. The number of elements sampled, would be proportional. So the size of the sparsifier is governed by the quantity sum of pi, and I have to argue that this is small, and I have to argue that the sampled object would be a sparsifier. Those are two things I'm going to do. What is going to be obvious is that if you don't care about the size, like if you just let it some pi be whatever it is, some pi as a size works up to log n is very easy to show. It's a natural application of matrix Chernoff. In fact, it is exactly the same proof as Spillman, Shrivastava, etc., etc. Okay, so the only new thing we are doing in some sense is giving you a bound on sum of pi's in terms of this connectivity parameters. Does it make sense? That's what we're going to do. Okay, good. So let me tell you what these pi's are, and then tell you how to bound them. Okay. So first, what we're going to do is bring everything at the same scale. Right now, like this AIs operate at various scales. They can have very different eigenvalues and so on. Just normalize by, so like look at 80, multiply both sides by, on the left and right. So conjugate by 80 to the minus 1/2. Assume 80 is full rank. If not, work on the subspace that it operates. Okay, so inverses exist without loss of generality. And now take 80 to the minus 1/2, apply on both sides. What does this operation do? Well, if I apply on both sides, the left-hand side becomes identity, right? So without the loss of generality, we have a sum of PSD matrices that add up to identity. This is like saying that, I have some kind of a normalization, okay? Once you are in this normalization, I can define the leverage score as simply the spectral norm of that term. The spectral norm of the normalized, AI, okay? You should feel at least a little bit a little bit motivated, in terms of what this quantity actually means. If the spectral norm is very large, imagine what happens if the spectral norm is 1. Okay, then I claim that you cannot drop that AI. Okay, why not? If the spectral norm of AI is 1, notice that AIs, I'm going to call AI and AI tilde the same because we're just going to assume now that they are the same, right? They're normalized properly. We know that their sum is the identity. Okay, and their sum, because it's sum of positive things, in any direction only adds. So if the spectral norm of one guy is 1, it means that everything else contributes 0 in that direction. So if I don't keep that AI, there is one direction, namely in which the spectral norm of AI is achieved, will not be covered. It will in fact be 0. So you can see that if the spectral norm is 1, at least I must keep AI. So you can see there's some notion of how important AI is to the to basically the spectrum of this sum of AIs. And so maybe it's not so unnatural that this is some notion of how important it is, even when AIs don't have spectral norm 1. Okay, does it make sense? Good. All right. So that's our notion of importance. Okay. Notice that all AIs can have large spectral norm because the directions could be very different. Right, like A1 could be large in one direction, A2 could be large in some other direction. This is like saying that some edge contributes to some cut, some other edge, some other edge contributes to some other cut. They're both basically super important. You can't drop them, but they control different cuts. Right? So sum of the spectral norms has no obvious bound is what I'm saying, even though the sum of the matrices is identity, because these can all be different directions. So the challenge is going to be what is the sum of this AI, like the spectral norms of AI. But, before that, I'm simply going to say, this is a very, very natural proof. It's the one that if you read the concentration inequality, it writes itself. You can use the proof to show that I can get, now, by the way, in this normalized one, I only care about additive approximation because I've normalized things so that all of them are up to identity. And you can show that, if I lose the log n over epsilon square on the sum of the importances, then the sampling scheme just works. So sample AI with probability proportional to the spectral norm of AI, so that the total number of things sampled in expectation is log n over epsilon square times sum of AI, the spectral norm. Then, this one works simply by a naive application of the matrix Chernoff bound. Okay? Does it make sense? Good. So I'm not going to give you a proof of this, but let me answer Chandan's question from before. The weight is simply 1 over the probability I'm sampling. Okay, so it's very explicit. And like I said, it is basically proportional to the importance. Okay, good. All right, so the main thing to prove is why is the sum of the importances small? Why will I not sample too many elements? And I want to relate the size of the sparsifier I'm constructing, some of the importances, to this connectivity parameter, this qualitative notion of being covered, every direction being covered or something. I'm going to relate that notion to this. Okay. So I'm going to be sketchy, but really, the sketch is, I promise you, if you try to make it a proof, it will work. Okay. So it's not sketch in the sense that I'm cheating you. Okay. So our goal is to bound, the sum of the spectral norms. We are going to assume everything is normalized. So, they sum up to identity. So that's my goal. Okay. What I'm going to do instead is fix an eta. In fact, I'm going to do this over all eta. You can think of this as like computing the integral by doing some Riemannian sums or whatever. Right? So I'm going to take some eta as a barrier and then count the contribution to the sum of the importances, all of which are larger than eta. So contribution of those things which are larger than eta, and then I'll do it for like eta over 2 and so on, and then sum them up. This is my strategy. Okay. So, hopefully you don't, think this is too unnatural. This is quite a natural thing to do. Like, I have numerical quantities. I want to kind of make them Boolean. That's what I'm trying to do. I want to think of them as whatever. They're at least somewhat large in some sense. Okay. So let's just focus on this part. Hopefully you don't mind that, there's not much gap from here and the whole problem. Okay. Yes, exactly. Yes. So, I'm going to need, so eta is going to vary diagonally, but yes, you're right that I'm going to lose log m here because I need to go polynomially small. Yes, absolutely. Okay, good. So, all right. So what I'm going to prove to you, or I guess I'm going to sketch to you, is a bound on the sum of the importances. And in fact, I'm just going to tell you how many of the AIs have spectral norm at least eta. Okay. I'm going to prove that the number of AIs that have spectral norm at least eta is at most 1 in eta. That should not surprise you. 1 in eta is like the right scaling times this n quantity with alpha as the parameter. So alpha as the this attenuation factor on the left hand side divided by alpha. Okay. So this is going to be true for every alpha. Okay. This is not written. Yeah, I guess. Yeah. So there is a for all quantifier analysis. For every alpha less than 1, I can give this upper bound. Okay. Eventually, that's why this bound is in some sense the best if I take alpha to be a constant. But we're not always able to bound this n alpha quantity when alpha is a constant. So sometimes we use this bound when alpha is 1 in log n or whatever. But the right thing to do is really just make it a constant. Good. Yes. Yeah. Nothing. In fact, you'll see even more so when I show you how we argue this. Okay. Good. So, and this, said already observed, we're going to lose a log m on top of this in order to get the whole bound. Does the bound make sense? Yeah. Okay, good. So let me give you some intuition now, why it's going to work. So with this normalized matrices, let's look at this, elements which have spectral norm at least eta, right? What does it mean that the spectral norm is at least eta? For every AI, there is some direction. It's going to be different in principle for every AI, but there is some AI, there is some WI, such that if I take the quadratic, these are unit vectors, so the normalized. The unit vector says that the quadratic form of AIs on WI is at least eta. That's what it means, right? Okay. So there's some witness vector that witnesses this high quadratic form. Okay, good. So now, assume. I'll argue why you can assume this later, but assume, so you have this bunch of AIs, right? Imagine that I get a subset of elements such that for each AI there is a WI, such that the quadratic form is at least eta on that WI. But if I compute the quadratic form of AJ on WI, meaning if I take the witness of one but apply it to another, then the contribution is very small. Okay. Then I claim that from such a configuration, you can derive a lower bound on this n alpha quantity. And the intuition is very, very simple. Okay. The intuition, I don't understand what Raghu is trying to do, but I'll just tell you what the intuition is. So the intuition is there is a direction in which AI needs to be large, but every other term contributes a small quantity in that direction. So the only way I can get the contribution I want in this direction is by keeping that AI. Okay, does it make sense? So I'm basically like, constructing this, like the analog of, you can think of it as like I'm constructing a bunch of edges and a bunch of cuts to go along with them, such that that edge is a main contributor to that cut. In fact, amongst this list, no other edge contributes to that cut. I have this matching between cuts and edges, so that each edge contributes to exactly one cut, right? And the cut size is small, so that edge is needed. Now, this configuration is clearly a lower bound on how many elements I need in the sparsifier, because if I drop any, I'm in trouble. I'm not covering some cut. That's exactly what I'm going to do, but in this, more numerical, abstract PSD matrix setting. Okay. So the only question is, how do I find such a set? How do I find a collection of AIs along with witnesses, such that the witnesses, obviously witness a large quadratic form, but are small on everything else? Okay. It's entirely just sampling. Okay. What's the idea? Look at WI direction. I don't know what's going on the slide, so I'm going to tell you. So look at the direction WI. Okay. The quadratic form is at least eta of AI. Okay. And I'm only looking at all AIs that have, contribution at least eta. Because the sum is 1, there cannot be more than 1 in eta things that contribute to this direction. So if I now sample at the rate of roughly eta, sample from this set S eta at the rate of eta, I should expect at most like roughly one element that I sample from this list, everything else will go away. Okay, so you need to do this a little bit carefully, and you need to do some pruning and all that, but you already see the intuition. In any direction, there are like 1 over eta things that could possibly contribute. I'm going to sample at the rate of roughly eta over log n, but who cares? And then, I'll get one, but no other. And if I don't get any of the others, I don't get any contribution. That's it. Okay. So you can see like it's, I promise you that you can make a proof out of it. And I hope you believe me now. Like it's entirely just sampling. Okay. Good. So good. Yeah. So yeah, like, if I get too big a set like this, I'll contradict the n alpha bound. And so it's going to be, so like, I sampled S eta at the rate of eta, and I can produce roughly the set. So I know that eta fraction of S eta can be upper bound in terms of this n alpha. So I have a bound in, bound on this S eta set that I cared about. Okay, that's it.
Definition was a bit stronger, right? That for every set of size k, there was one AI which was alpha dominated by the.
Yes.
But when you're applying it, you're actually applying it for like in a distribution. So you're saying if I sample a set in that, so there's a like application is slightly more relaxed. I mean, I'm not sure.
You're absolutely right. I mean, maybe the way to think about it is that that's one place where we lose a logarithmic factor, etc. And you could argue that we wouldn't need it, or we could be more careful.
But like, I mean, this is first the only place where the n like the
yes,
like the n measure has.
Yes. Yes, exactly.
Showing up in a distribution sense. Like
yes.
If I draw a set, then
yes,
it should have a property
yes.
rather than
yes. Yeah, absolutely. I mean, I can come back at the end on some speculative aspects, but basically, like, you are absolutely right to observe that, the proof, what you're observing is in some sense one sloppiness in the proof. And you could argue that maybe you could potentially improve the bounds, by being cleverer about it. Okay, so what have we done so far? We first proved that the sparsifier size with matrix Chernoff can be controlled up to log n by the sum of the spectral norms of these normalized AIs. We gave a bound on the sum of the normalized AIs in terms of the number of AIs, log m, R is m, that part I'm certain, times this n star quantity. And so overall, we basically get the theorem we wanted. Okay, so this part is very sketchy and, I have only 3 minutes, so I'll be quick about it. But basically, the main lemma is to bound this n alpha quantity for Cayley graphs, but the intuition is exactly what I already told you. The fact that you can generate, any group element by linear combination, and that's just the counting argument, okay? So this is this routing fact I was telling you earlier, that, I can somehow replace a group element by, the rest of the elements in this set T, as long as set T is like at least logarithmically large. This is simply using that, I can cover some GI by the rest. And the log comes because the length of the path is log. So if you've ever seen some very simple latent row style, routing, well, that's what this is. There's nothing very deep going on here. So good, yeah. So basically you get a bound of logarithmic bound on this. Because you lose log here, you get a bound of log on n 1 over log of this matrices coming from Cayley graphs. And so that gives you a bound of log square on n star in the way we proved it. So we got a log square bound here. We lost 2 logs, in our analysis beyond n star. So in total, we get a log to the 4. Good. Yeah, so that's basically it, okay? So let me maybe end with the speculative things. Can you hope to get a BSS-like theorem? Can you remove the logs? And it goes in the direction of what Siddharth was asking. The proof is super simple. I think I almost gave it to you wholly in some sense. Maybe you can't produce log to the 4 exactly with it. Maybe you'll get like 1 more log, etc. There are some tricks here and there, but modulo some log tricks, I think I told you everything. So you can see it's very simple. You can ask, can I build some more complicated machinery, sophisticated machinery like, the barrier method, where I don't independently sample AIs, right? Like I can do something more global and beat the kind of bounds we're getting. In particular, can we hope that this quantity, in fact, is a characterization? I can tell you offline, what we know about it, but that's a natural question. You can even ask, when is n star a characterization? If not for all families, can you, tell me more about the families where I can expect it to be a characterization? You can also ask, can I just solve this Cayley sparsification problem correctly? It's a very natural question, right? Maybe we can expect a full answer to it. So, it turns out that, you can prove. So let me maybe say one point which might be interesting to people who have thought about Cayley graphs a little bit. So I told you that in abelian Cayley graphs, you can't expect to beat log n because, you can't even construct expanders, without log n generators. But there's this notion of so-called quasi-random groups where, generic generators, constant number of them, do generate expander graphs. And there are theorems like this. For example, there are famous sequence of works with Burgen and Gambert that show that these matrix Lie groups like, the orthogonal group, SO3, etc., they have this property. In fact, you can generate expanding Cayley graphs on these groups in the appropriate sense. They're infinite, but you can do it, with just constant number of generators. So you might ask for these quasi-random groups. For those who know representation theory, a group is quasi-random if, the minimal dimension of its irreducible representation is polynomially large in the size of the group. So it has very large representations. Abelian, abelian Cayley graphs have one-dimensional representation, so they are super non-quasi-random. This is very opposite of abelian. You can think of it as very non-abelian Cayley graphs. You might expect that maybe for those kind of groups where expander graphs can be constructed with constant number of generators, maybe you can beat this bound. Turns out that sparsification is significantly harder in the sense that you simply cannot expect that to be true. Turns out that for any group, including quasi-random groups, you can prove that n star is at least square root log of the group size. This is also, by the way, very easy. It comes from a theorem of Erdős, actually. I mean, the bounds were improved later on, but it turns out that in any group, you can embed an abelian group. Okay. And then it turns out that you can use that embedding to produce a bad set of generators. And then if I ask you to sparsify that Cayley graph, you are in trouble. Okay, so basically, like, if you thought that maybe we'll get lucky with quasi-random groups and improve these bounds, it turns out not so. All right, that's all I have to say. You can take questions. Oh, wow. Thank you. Does it have IISc written on it?
Yeah, probably. Yes.
Okay, that's good.
I think in big letter.
Okay, that's good. Thank you.